Hello, and welcome to our discussion of Theorem 1.4.20. Let's state our hypotheses and then the result of the theorem. We'll take I to be an interval in the real numbers. We'll take functions a1, a0, and g to be continuous on I. And we'll take points y0 and y1 that could be complex. They'll be our initial values. We will set af to be f double prime plus a1 of x times f prime plus a0 of x times f, and we'll fix a point x0 in I. And if we do all that, the initial value problem, whose ODE part is the operator a on f equals g, and whose initial values are f of x0 equals y0 and f prime of x0 equals y1, this initial value problem will have a unique solution that is twice continuously differentiable on I. And our proof of this theorem is a good summary of the techniques, both concrete and abstract, that we've learned in this section. In particular, it will review how we construct a solution to an initial value problem, and it will also go a little further in proving absolute uniqueness. So let's begin. First thing is we need to look at the homogeneous problem. Lemma 1.4.12 tells us that A has a fundamental solution set consisting of the functions j1 and j2. By this I mean the set j1 and j2 is linearly independent. j1 and j2 solve the homogeneous problem, so a on j1 is equal to a on j2 equals 0. And j1 and j2 span the kernel of A in the sense that if a on f equals 0, then f is equal to c1 times j1 plus c2 times j2 for some constants c1 and c2 in the complex plane. And variation of parameters tells us how to solve the non-homogeneous problem. The formula of variation of parameters, which is highly worth memorizing, tells us that if we know the fundamental solution set, then we can cook up a function f0 that's twice continuously differentiable on I, such that a on f0 equals g. And of course, if the operator a is constant coefficient, we know how to, through the characteristic equation method, construct explicitly the functions j1 and j2. And if a has variable coefficients, then we hope for the best, and we'll learn a little more about that later in the course. So we know how to solve the homogeneous problem, we know how to solve the non-homogeneous problem, now we have to build in the initial conditions. Remember, variation of parameters alone doesn't guarantee that the function f0 that variation of parameters gives will solve the initial conditions at all. Instead, we'll seek a solution of the following form. F of x equals c1 times j1 of x plus c2 times j2 of x plus f0 of x. And I know j1, j2, the fundamental solution set, and I know f0 from variation of parameters. So as always, I just have to figure out what are c1 and c2. A good check on our work is that a function of this form does indeed solve the non-homogeneous ODE part. If I apply A to the linear combination c1, j1 plus c2, j2 plus f0, this turns into c1 times a1 on j1 plus c2 times a on j2 plus a on f0. A on j1 and a on j2 is 0. A on f0 is equal to g. I get 0 plus g equals g. So a function of this form does solve the non-homogeneous equation. And I just need to find now c1 and c2 to match the initial conditions. As always, I like to start by differentiating. I'll calculate f prime of x is c1 times j1 prime of x plus c2 times j2 prime of x plus f0 prime of x. And then to fold in the initial conditions, I want y0 to be equal to f of x0. So that has to be equal to c1 j1 of x0 plus c2 j2 of x0 plus f0 of x0. And I want y1 to be equal to f prime of x0. That's c1 j1 prime of x0 plus c2 j2 prime of x0 plus f0 prime of x0. Now in this expression here, in this system of equations, I know what j1 and j2 are. I know what f0 is because I constructed it explicitly from variation of parameters, and y0 and y1 are given to me at the start of the problem. So in curly braces here, the only things I don't know are c1 and c2. And this pair of equations rearranges to a linear system for c1 and c2, In matrix vector form, it looks like J1 x0, J1 prime of x0 in the first column, J2 of x0, J2 prime of x0 in the second column. That matrix times the vector of unknowns C1, C2 is equal to the vector of known numbers y0 and y1. So if I can invert this matrix, I can solve for C1 and C2. And if I can invert this matrix, I know the C1 and C2 that I find will be unique. Let's check the determinant. The determinant of this matrix is J1 of x0 times J2 prime of x0 minus J2 of x0 times J1 prime of x0. But that, of course, is the Wronskian of J1, J2 at x0. And we know something about the Wronskians of fundamental solution sets to differential equations. This Wronskian is never zero. So our matrix is invertible. We can uniquely solve for C1 and C2. And now we have shown that the initial value problem has a solution of the form f equals C1J1 plus C2J2 plus F0. Now let's be careful with the uniqueness result that we said when we inverted this matrix. Given the non-homogeneous solution F0 and the fundamental solution set J1 and J2, the numbers C1 and C2 are unique. You can't plug in different numbers for C1 and C2 and solve the initial value problem and the differential equation at the same time. But is it at all possible that the initial value problem has a solution h with h of x, x not equal to f of x? Maybe h has some totally different form that doesn't involve linear combinations of J1 and J2. I claim the answer is no. What would happen if you had another solution h? Well, you'd solve the initial value problem with f, a on f equals g, f of x0 equals y0, f prime of x0 equals y1, and you'd solve the initial value problem with h, a on h equals g, h on x0 equals y0, h prime of x0 equals y1. We're going to do our old trick of subtracting. Let's put phi equal to f minus h. So linearity of the initial value problem means that a on phi is equal to a on f minus a on h, which is equal to g minus g, which is equal to 0. And phi on x0 is f of x0 minus h of x0, which is y0 minus y0, which is 0. And phi prime of x0 is f prime of x0 minus h prime of x0, which is y1 minus y1, which equals 0. So what does this mean? If the initial value problem has another solution h, maybe allowing for different kinds of functions in the linear combination, not just J1, J2, and F0. If the initial value problem has another solution h, then I look at the function phi equals f minus h, and phi solves an initial value problem, a on phi equals 0, phi of x0 equals 0, phi prime of x0 equals 0. Lemma 1.4.7 tells me phi equals 0. The only solution to the initial value problem with 0 in the non-homogeneity and 0 at both initial conditions is phi equals 0. And this, like the existence of the fundamental solution set, was one thing we had to take for granted. So what does this mean? F equals h. Our solution is unique. And we are done.